Hi, everyone. Thank you for being here. So today we will talk a little bit about profiling your AI/ML application using NVIDIA system tools. We would take a look at the Nvidia-Nsight systems and NVIDIA compute system. So I believe lots of you were on the NVIDIA profiles talk yesterday. And there, Robert did a pretty good job showcasing different things that NVIDIA tools can do. And today we would like to see those hands-on. So our goal is to try to do some hands-on activities to see how we get these type of things from Polaris, for example. Set up our things so that we can bring them back in and look at those locally. So why would we like to do profiling? So profiling gives us a better understanding of what our applications are doing under the hood. And we get a clear picture of our execution of the application. And by looking at those, we might identify bottlenecks. So if we are AI/ML people, we can then go and talk to our developers saying that, see, my communication kernels are spending way more time than my compute kernels, and I'd like you to do something about it. Because we start with basically pre-built workflows, and we try to build on codes that has been already there, tried and tested, and we try to modify them to our needs. So from that perspective, if we look at profiling, it's a useful tool to have if we can get a high-level overview of what the application is doing without going inside the application and making little changes to track things that might be interesting to us. Okay, and so we have two tools, Nsight Compute for kernel-level data and Nsight Systems for system-wide data. And how we are going to generate the report, we will be doing that through our hands-on activities. The first thing that we will be doing, we will be trying to download the Nsight systems and install on our local machine. Also, the Nsight Compute in our local machine. And I have tried to put a whole workflow in the AI/ML profiling repository. So if you go to the main repository of the workshop, you will see a folder in the master's branch called AI/ML Profiles. There, I have put together the workflow and scripts that we will be running today. So this is how the repository looks like. So have you all been able to access this, and do you see this README page? Folks? Yes, good. So what we will be trying to do here is we will be trying to profile a simple PyTorch example. And what does this PyTorch example do? This PyTorch example actually mimics sequence parallelism. So this strategy is very similar to the sequence parallelism strategy that we use for our Aurora GPT training. And a very similar implementation is adopted in Megatron DeepSpeed as well. So what I have done is I have tried to identify the key compute and communication steps. Compute and communication steps, and make a simple example out of that. So, and that example is written using PyTorch, and this is in the sequence parallelism compute.py file. And what we do there, we start with a distributed sequence. You can imagine this as the input to one of your transformer layers. And then we all gather them, do two matrix multiplications. You can think of them as applying your model. And then once we are done doing matrix multiplication, we reduce scatter them. People follows? So this is considering that we have a fixed degree of tensor parallelism and fixed degree of data parallelism. In a real life application, we will change all of them and we will play around and come up with a strategy which makes our training time the smallest. Questions? Okay, so now we will try to run these using job submission script that I have put in there, and the users have to be careful in setting up the directories that are there, which I have put in so that different profiles go in different locations, etc., etc. And now to do the profiling, I have set up 2 wrapper scripts, which we wrap our application around with, and then we launch through the QSub. So this will be our basic strategy. Make sense? And I'll take 1 more minute before you can dive into the hands-on. This command is, can you guys see okay? This is an MPI exec command. This command will be our main workhorse throughout the hands-on session. We will be running this MPI exec and wrap this nsys profile command around our application and launch it. Okay? So this sequence we should have inside our head. First we have MPI, then we stick in the profile, and finally we have Python. Okay? In principle, if we swap MPI and the profile bit, it should work as well. But then we will have data for MPI communication, which if we are interested in, we can get. But in this strategy, we will get data only from what our application is doing. Make sense? Okay, so now we will go to the hands-on, and I will try to run these commands, and I will request you guys to follow along. So you have, how many people have Nsight systems or compute installed in their machine? Only 1, 2. So do you think it would be useful if you try to install it and go through the whole workflow? Or should I go and try to launch these things and show you the results? Which one do you like better? Number 2. Okay, fine. So now let's go to, okay. So before going into that, let's just look at our Python application before I start running things.
We're supposed to run it on Polaris?
Yes, sir.
We're going to run it on Polaris?
Yes, that's the plan. So this one has a whole bunch of things that I tried to say about what I do, but the most important thing is we import MPI for Pi, we import torch, whole bunch of arguments. We set up the rank and world size. These are important. The world size is basically over how many ranks we'll be deploying this application. And then we set up some other things. And then we come to the main loop. So in this loop, we first do torch distributed all gather into tensor, all our distributed sequences gathered into one tensor. And then we do a matrix multiplication, we do another matrix multiplication, and then we reduce scatter the tensors back to all the ranks. So this is the heart of it. Okay. So now, yes, please. Yes. Oh, so I use this synchronize so that I can get my timings correct. So I try to time the individual operations. So I start a timer, do the timing measurement, start a timer, do the computation, synchronize until all of the similar type of computation is done, and then take my timer measurement again. So this is just to get my timings correct, because Python is imperative, so I force it to wait until all the compute is done. So now once we have that, here is my submission script. Submission script starts with the PBS directives, and this has information that needs to be changed for an user. I set up my different directories. I look at the environment variables, etc. But this is the final command that does it for us, as I have shown before. MPI exec, number of ranks per node, etc., etc. Python, my application, and this is the arguments that I pass to my application. Now, final bit is how do I put the wrapper in? So this wrapper contains the information about the profiler. What type of options we are going to use, how many ranks of multiple ranks we are going to trace, etc., etc. And as I said before, I stick it between my MPI exec and the Python call. So the sequence to remember: MPI exec, profiler, Python. That's it. Even if we do not give any other options, by default, it should print out something for us, which will be useful. And now, one final thing, we go inside the wrapper. What this wrapper actually do, it sets up different directories and tags, but the most important thing is it runs a bash loop, which sets up how many ranks we are going to track. So we are going to track rank 0 from each node. Okay, and we will track ranks only up to 8. So that means if we have total 8 ranks running, we will trace rank 0 and 4 out of those 8 ranks. How do I come up with this number 8? We have 4 GPUs on a node, and we will be running 4 ranks per node, and I want to trace 0. So globally, the rank count goes from 0 to, so it's 8 ranks, right? And each node will have a rank 0. In the global count, that should be rank 0 and rank 4. I'm talking way too much. Let's move on and try to get these things going. Okay, you guys can read some. This is my terminal, okay? And the first thing that I am going to do is I will try to q sub, which one did I change? I forgot. Q sub insys. Yes, I have.
Yeah, can you show the users where you need to make the changes in the file? That
Yes.
way they can do the
Yes,
Q sub as
exactly. So -q should be changed to hands-on HPC, right? Because that's the queue on which you will be running on. Allocation -a should be changed to ALCF training, because that's the allocation. And then we have to change the standard output directory, the directory where PBS should send the standard output, we also have to change the standard error directory, where PBS should send the errors if there is any errors. Also, we have to change the work directory. It's where you have cloned the repository in. All the files are in the top level of the repository. And we have to set up a profile directory where the outputs of the profilers go. And we have to change I do not think we have to change anything else. The structure is such that inside the work directory, we should find the wrappers.
What about this temporary directory you have in the MPI exec command?
This that's a good call. Thank you very much. So this temporary directory is a directory that needs to be passed so that the profiler can generate some temporary data based on which it generates the report that we get. And we have to pass that through an environmental variable to our MPI exec call. You have to change those directories also.
Is it less confusing that you just change it and push it?
If I change those, sure thing I can do that. Of course I can do that. Okay, so now, but it has to be user specific though. So you still have to I do not think I have a way to make it very general for any user, but these are the directories that you need to change. Sorry, I will try to find a way around that. Make sense? Okay, so per se we have changed all our directories and they're in correct order. Then we queue sub our example to a queue. I think I have gotten started running. So this is basically a one node task with 4 ranks per node. And now if I go and try to look at the results that came out, hopefully it has finished. The job is still running, so it should not take very long. Okay, it looks like it's been finished. And then so this is how the output looks like. It tells us that it's been running on these 4 ranks. It's running with a bfloat16 data type. It has the sequence length to be this, hidden dimension to be this, precision type as bfloat16. So these are the arguments that user can change and play around with to see how it's going. And then it gives us a whole bunch of timings. The first all gather took however long, etc., etc. But the nice part is, see, it prints out lots of stuff, but the important thing is it prints out a summary of all the calls that has been happening. And important for us is these calls. These are gem kernels which are related to our matrix multiplication. So it tells us that we are spending 35% of our total execution time trying to do matrix multiplications. There is another one, 32% time we are spending doing another matrix multiplication. And then we have the all gather kernels spending 17% time, and then reduce scatter kernel spending 15% time. So these are all very expected, right? Our workload was a combination of matrix multiplication, all gather, and reduce scatter. Questions? Yes, sir.
Are these on each GPU or like some on one?
No, these are on each GPU. See, you can see, like, there are these rank numbers also getting print, 0 here. So it is tracking only rank 0 because we have a single node run. And we set up our wrapper script such that it tracks only the rank 0 on each of the nodes you run. We could run it to however many nodes we want, but our setup will allow us only to track rank 0. Clear? Okay, so now, if the thing has successfully finished what it started to do, we should see something like generated some NSYS report. Okay? And if I go and load up these reports, this is how they look like. And now, how do I improve the situation here? Does that look better? Okay. Yes. How did I load that? Okay, so what I did is File, Open.
So early in the talk, Khalid had asked if anybody had Nsight systems installed on their system, and only 2 people raised their hands. And then he asked, do you want us to just show you how to load it? So you need to install Nsight systems on your system in order to load these profiles.
By system, you mean virus?
No, this is on his
Your
local
local.
machine.
Yes. So it's like if you go to the README, I tried my best to write this as explicitly as possible. And my intention was to make all of you go through those painful steps. But then it's all right. So it's you go open, and then you go to a particular directory. You have your, so visual real estate is an important thing. So I have set all these things here, so small. But you have your NSYS rep file. You click on that. It allows you to load this and start showing you the bubbles and things, etc., etc. But that's basically the execution timeline of what is happening inside your application. Now, per se, we have loaded them. And in the left-hand side, we have a list of things that's happening. This particular data is from 2 nodes, a run that was run on 2 nodes. So you see 0, 0. That tells me it's node 0, rank 0. And then you cannot read. What am I talking about? But it's from a 2-node rank, and it gives us data from 2 GPUs, and we put them on top of each other. It's as simple as go to File, Open, and then you will have your 2 or 3, however many profiles there. You drag them, click Open, it sets it up for you. It's extremely painless, believe me. So we have these things, and one way of looking at the profiles is to look for repetitive patterns. So for example, if I zoom in really quick, and then not today, there we go. Okay, so I can see NCCL kernels being called. These are our communication kernels. NCCL is the communication library underneath. And then if I zoom in even more, I finally see the matrix multiplication kernels, which are called Ampere kernels. And if you look at that, you find that our matrix multiplication finishes in 450 microseconds, and communicating these results takes 36 milliseconds. That's not a good thing, because our computation is done way earlier than the communication. And that's why it's a benchmark. So this benchmark was trying to look at the communication aspect of these transformers and large language model training. So in a real life case, we will have another heavy matrix multiplication involved, which is the flash attention. How many people have heard the name flash attention? Attention. No, oh, I thought many people would have. Yes, question. Yes, please, go ahead. Oh.
The question is about some things that you said previously, and it might be a simple question. How do you know which kernel connects or represents which activity, for example, matrix multiplication?
So this is a very, very good question. What is that? So usually we look at the list of kernels. So use this thing that was printed by NSYS, right? It's a summary report of these kernels that's been called. We look at them, and then we go to the docs and find out what is this kernel is. GEM kernel is a very popular kernel. It has been around for a while, so we immediately know this is, but there could be kernels which you are not familiar with. And our only resource at that point is to go look at the docs and probably try to talk to the developer folks to find out what's going on. But usually, although the kernel names are fairly complex, there are things in them which makes it somewhat identifiable. So if I zoom in really quick here, you will see it's written as NCCL dev kernel all gather. So it's all gather is a popular thing. For example, it's an MPI collective that people do. So you know, okay, this kernel is what underneath from the software stack was driving this for you.
Yeah, and another answer to that question is when you're doing these type of profiling, it would be best, like with the profiling tools, if you could capture the full call stack. So I think in newer versions of NSYS, you're able to capture the full Python call stack as well as the CUDA kernels that are being called underneath. So you'll be able to see from the report, oh, these are taking the most time, and then correlate that to the timelines that Khalid is showing in the other view on the NSYS window.
Yeah, Nsight systems.
You'll be able to go up the call stack and see, oh, this Python function is calling these lower level functions.
Questions? Okay. So now we have, like, for example, identified one of the kernels that we are spending a lot of time trying to, while running our application. And there are lots of information here, but I just tried to focus on the GPU parts of it, because in this simple example, the CPU work is pretty minimal. I just make an array and then offload it to GPU. So, but the GPU does the heavy, however much compute is there. But it's also a fairly light compute, but more communication heavy benchmark. But we can change that anytime we want. We can change that by increasing the precision. So this is bfloat 16. We can crank it up to FP64, and this will, in some respect, become a heavier compute. We can increase our matrix dimensions, it will become a heavier compute. We can make our matrices bigger, it will become a heavier compute. So these are the decisions that we get to make if we are trying to design a training strategy from scratch. So usually we would get a training strategy that has been used by, for example, Megatron Deep Speed, and we will work with that. But if we had to develop this from scratch, this type of profiling will let us know how to balance our communication and compute, for example, and how to set up our matrices, how to distribute our workload, so that at the end of the day, we have reduced training time, for example. Make sense? Okay. So now that we have identified a popular kernel, like, yeah, they call it hot kernels. But now that we know that we have a kernel where we spend a lot of time, we want to know how that kernel is doing. And that we can do by running the Nsight compute profiler. So let me go and change my okay, what are we supposed to change? We are supposed to change the queue name, Hands-on HPC, and we are trying to change the allocation, ALCF. Hopefully I do not mess up the scaling. And we will be running this in one node. So this change is not as scary. You just have to do it once and get the muscle memory, and then it becomes pretty automatic. Okay, so we are running with 4 ranks per node. We'll be again tracing rank 0 only. And now I want to take a look at the NCU wrapper. So what is there in the wrapper? So it's very similar to the NSYS wrapper, but we have just a few things that are different. Profiling a GPU kernel for its compute activities is fairly time consuming. So if we want a little bit of a quick turnaround, the strategy would be to profile them one by one, but we can definitely profile however many we want together. But to make it more bearable from the user side so that we get responses back from our computers, we should go one by one. So we set up the kernel name here and pass that with a -k option to our profiler. And there are 3 different options that is more frequently used. One is the detailed. So this detailed option actually pick and choose standard set of compute metrics for you. The option roofline, choose a few GPU metrics that are related to your roofline plot, tells you whether your application is compute bound or communication bound, stuff like that. And then you can obviously do full, like everything in full glory. It will be a big profiler output, but we still can manage. We have fairly beefy laptops these days. Okay, so now that we have taken a look at that, let's go and try to, Okay, try to launch this. I hope I do not get. Okay, it started running. I go and take a look at my standard out. 067216. Okay, it has started profiling this. Can you see? No, of course not. So it is telling me that it's profiling the Ampere BF16 gem kernel in different stages. So the profiling, the way it works, it runs different paths of your application because it's collecting different metrics at certain sampling frequency so that it can construct a nice, good-looking graph for us. This can be fairly time-consuming. With respect to this application, the total runtime for this application is in the order of seconds. But with the kernel profiling, just one kernel, it takes roughly about 5 minutes. So you can imagine trying to do it for multiple kernels, et cetera, et cetera. Okay, so now I have done this exercise previously, so I have a couple of them pre-made, and if I go back to my Nsight compute window, this looks like this. And can you guys see? You see bars and charts only. Okay, so there are several sections here. The first one that I clicked on, can I zoom in? For some reason, I cannot zoom in to this window. Okay, so there are several ways of looking at the data that they have collected. I find the second tab, the details tab, to be nicer. In a sense, it gives me quick information about how that particular kernel is doing on the device. And on the right-hand side, you have this menu that pops up. It gives you three things: your GPU throughput, which is very important in my opinion. It tells you how much of the available compute is used by your kernel. It also tells you how much of the available memory is used by that kernel. So this is pretty nice. So, and if we look at our kernel, the BF16 gem kernel doing the matrix multiplication, we see it is using close to 90% of the compute available, which in my opinion is expected because these are highly optimized kernels provided by the vendors. We are just calling a library. It's not like that I sit down and write my matrix multiplication routine. And then it is doing okay memory-wise. It's using roughly 50% of the memory. And this is kind of expected too. My matrices are fairly small. It's not pretty big as well. Next comes the workload analysis part, which is very nice because it tells me, okay, my BF16 matrices are using tensor cores to get the computation done pretty fast. If we look at the same application run on FP32 and look at the same tab, we see the tensor cores are not being used. So what did we learn? We learned about a feature in Nvidia A100 GPUs. If you are running an application with FP64, you will be using tensor cores, bfloat16, and any of the int, you will be using tensor cores. But if you are running with FP32, you will not be using tensor cores. So here comes another design choice, and we get to choose for which operations we should use which precision to make a balance between the correctness of our calculation and the performance that we are going to get. Obviously, from the AI/ML side, using the pre-built workflows and Python codes, our job becomes talking to people who can make these changes for us. But we have a fairly good control over the communication aspect of things. We can think about which collectives or set of collectives we should use to make our data movement friendly to the network setup that we have. Thumb rule is try to minimize communication, maximize. So these are the simple things. Okay, so now we go to our B-float 16, and we look at the roofline plot. If we look at the roofline, this one sits right here, and it's getting 46 teraflops per second, which is pretty low because and also my input size is such that it does not saturate and does not reach to the peak level of flop. The calculation is done even before it reaches its peak capacity. So in an ideal benchmark should run, however, a certain amount of time so that the GPU can. And my calculation and workload is pretty small. How do I know that? I know that by looking at the, where is the occupancy graph? By the occupancy. And you see that my occupancy is only like 10%. So my GPU remains busy for a very small amount of time. So that means what can we do? We can increase the batch size. Here in my example, I have put batch size equal to 1. Not a good idea. Make the batch size bigger, put the workload there, and then once you have made the batch size bigger, you have to probably look at the learning rate and also loss convergence, and you start slowly optimizing your workload. So these are basically what I wanted to say roughly. Any questions? I imagined this session to be like a good workout session for me. I thought there would be lots of running around. But questions, please. Feedback is welcome too. What could I do better? Halloween costume. That's a good idea. Thank you. Oh, we're 31st. I could have done Halloween costume today. Yes, I think, yeah, I have covered what I.
All right. Well, thank you, Khalid, for showing us a little bit of how to use these profiling tools and when we're running our Python applications.
And just before leaving, I'll be hanging around here. If you have an application that you would like to hook up with a profiler just to get something quick and dirty, I'll be hanging around here. And just like, I think that you will have the access of these slides, and I do have my email there. Just send me an email. I'll be very happy to talk. And I am really interested in setting someone up, actually trying to do this thing, because in action, many things can go wrong. So it would be a rewarding experience for me if I could set someone up trying to do these things hands-on. Okay, thank you very much for your attention.